So I'll try to keep this snappy. So earlier this morning, Professor Diwar gave a talk about these top-down approaches to dealing with fluid turbulence. So just briefly, the bottom here is essentially the GCM paradigm, which is essentially you resolve the equations to the maximum resolution the computers can handle, and you chuck in all the other physics you need, clouds and so on, and then you just run these massive simulations and average things out afterwards. So yeah, that's obviously practically a massive pain, but it's also, you're still sort of, you haven't got the full continuum model in there. As many people have pointed out, it's still essentially a discrete model, and there's subgrid resolution stuff that you're also essentially guessing, making empirical fits and so on. So we're sort of looking at a more, I guess, systematic way of doing things, where you start at the beginning, recognizing you're going to be averaging out microscopic processes, and you try and do things reasonably from the start. So, you know, from a practical perspective, that would be great, but also in terms of our conceptual understanding of essentially the crucial physics that goes into turbulent processes and so on, and it would be really good if we could make some progress on that. So this figure is a set of data on pipe flow, so just pressure-driven flow in a pipe from a little while back. The thing I just wanted to draw your attention to here is that these profiles here are essentially, they're very easy to reproduce in different labs and so on. So despite the fact that, you know, we talk about all the complexity of turbulence and so on, there's a definite sort of regularity to it that's actually quite striking. Like, for example, this is of a range of 3 orders of magnitude of the Reynolds number. And you can see here this like sort of logarithmic sublayer is consistent across all of those. It's just how they peak that's different. So there's a lot of sort of regularity in the average properties of turbulence. So perhaps it's not unexpected that there might be a simpler cause to that. So I'll just kick off with some physics. So this is what's known as channel flow. So these black lines represent sort of infinite planes. And you impose a constant pressure gradient that's pushing the fluid between the planes. This sort of weird squiggle is meant to represent a kind of a velocity profile, but obviously it's in 3 dimensions, so it's doing this in all ways. And that's going to be jiggling around because in the turbulent regime. And so that's the Navier-Stokes equation for an incompressible fluid. I've divided everything through by density as usual. All right, so that's the basic system. And to study those sort of reproducible mean properties, you introduce what's known as the Reynolds decomposition. So you sort of average the jiggling bits out and look at and decompose it into this sort of stationary mean flow and a residual V, which is the difference between the jiggling bit and the mean flow. And you also have a pressure. For some reason my line is weird there. So the pressure's also got a jiggling bit. And you can do this decomposition by simply taking a spatial average in the planes parallel to the boundary conditions. So this is just a plane average over this S. And the basic equations you get out, you can split them into the equations for the mean part and the fluctuating part. And the mean part, as you can see, it's exactly the same as the original Navier-Stokes equation, except you've got this thing here, which has got these, what are known as the Reynolds stresses in them. So in other words, the mean flow, like the turbulent eddies, influence the structure of the mean flow. And getting a handle on that term is the reason that it's not straightforward to use this equation to just solve for that mean flow. Because, you know, to get the turbulent eddies, you need to solve all this junk. So in a paper a little while back, Malkus suggested this principle where you don't look at those turbulent eddies at all, and instead you just maximize this sort of objective function which is the kinetic energy dissipation of the mean flow. So it's basically just the sort of average gradient. It's like a measure of the average gradient of that profile. But yeah, physically it's the kinetic energy dissipation. So you maximize that thing subject to Rayleigh's criterion. So this says there's no inflection points. In other words, if you look here, he doesn't admit profiles that could sort of go back and forth, that kind of thing. It has to be a sort of nice smooth hump. And then this other sort of technical condition on the smaller scale of motion. And he only considers flows with constant Reynolds number. So you'll probably be familiar that in like plane flow like this, pressure-driven flow, the laminar solution is actually quite a bit quicker. It has a higher Reynolds number in principle. Well, it's unstable, but so he's considering only flows with the same Reynolds number. And when he does that, you get this lovely fit that Professor Diwar showed this morning. So here you have the data in the dots, and these are two sort of slight variants of the solution, this maximal solution, based on slightly different criteria for this boundary layer stability. So this is quite incredible. I mean, people argue about von Karman constants and so on. I've been doing that for decades. And this thing just is a very straightforward procedure. It's really not very complicated. You get this. Okay, so why on earth should you do that? And Malkus provided this interesting sort of stability argument, which is really what I want to talk about. It doesn't help us very much if we just can do a procedure and it works without understanding why, and I'm hoping to sort of extract some meaning from it. So essentially, he considered the stability of two different steady profiles. So you'd have U0 with its Reynolds decomposition, and it's steady, it's unvarying in time, and an alternative, U1, with its fluctuating component. And you perturb the original flow with the fluctuating part of the alternative. It's a very strange thing to do, but just bear with me. So he considers doing that. And when you do that, you can go through some basic algebra using those original equations of motion, and you can show that this means that if the second flow had a higher kinetic energy dissipation, then the original flow would be unstable to that perturbation. In other words, he's found a perturbation that will break up this mean flow. Now, there's several problems with this. The first is there's no reason to suppose that this thing is actually a solution of the Navier-Stokes equations at all. You're just adding something to, they're not linear equations, so you can't just add solutions and assume that's a solution. So there's that. You can sort of go with that if you like. But also this argument is not intuitive at all. It's just a bunch of algebra. It doesn't sort of give you a feel for exactly why that might work. So we were kind of staring at this, and we noticed that if you write out, so in other words, if you just dot those Navier-Stokes equations with their corresponding velocities, you get like the energy equations. And if you write them out, you'll get these. So this is the kinetic energy equation for the mean flow. So its change in kinetic energy is the drive from the pressure, plus this thing, I'll talk about that now, minus its dissipation. The change in the energy of the fluctuation is this thing here, which is the drive from the mean flow here. So this is being lost from the mean flow and given to the fluctuation, minus its own dissipation. And the point here really is, it's really a simple observation, that the energy sort of enters the system from the pressure field. I'd prefer to use this anyway, yeah. So kinetic energy sort of enters the system with the pressure, and the pressure doesn't drive the fluctuations at all. The mean flow acts as a kind of a gatekeeper on the energy, and then it passes the energy on to the fluctuations. So by elementary reasoning, you can see that if the mean flow has a higher kinetic energy dissipation, there's less energy to drive fluctuations. So there's a very obvious physical reason that you'd expect mean flows to be to tend to have higher kinetic energy dissipation, just for stability reasons. Yeah, so this way of looking at it is a lot simpler than Malkus's argument, and it gives you a real feel for why we would be looking for solutions with maximal kinetic energy dissipation. It's also, I didn't mention that this argument that Malkus gave, the algebra involved is very specific to this configuration with parallel plates and so on, whereas this here, it's a lot more generic. So, for example, if you look at Navier-Stokes equations on a rotating sphere for, say, the atmosphere, so you've got to add in a Coriolis term, and you've got like body forces, basically. So that's gravity plus centrifugal acceleration. Okay, well, I'll get to that it works in a second, but okay, so yeah, so you just need to be a bit careful about the Reynolds decomposition in this case. So in the parallel planes, you've clearly got this kind of redundancy. The plane is kind of, the system is symmetric with respect to the planes. There's no reason to consider that detail. But in the atmosphere, you can't really get rid of any particular dimension without getting rid of a crucial detail in a sense, because the vertical level in the atmosphere, there's that like pressure gradient. Then there's temperature gradients in the meridional direction, and the Coriolis term sort of biases the velocity fields in one direction as well. So basically, you kind of you just need to notice that in the case of the plane of the channel flow, the horizontal averaging is sort of like an ensemble average, where each vertical section is sort of like an independent instantiation of a turbulent field. And so he's kind of got an ensemble average for free when he takes volume averages, whereas we just need to add that on explicitly as an explicit ensemble average, which I've tried to represent here with this ridiculous image of planets. So yeah, when you do that, you get essentially the same structure again. You have the global kinetic energy generation due to like pressure differences in the atmosphere. And again, the mean flow acts as a kind of a gatekeeper. The fluctuation can only be driven by the energy it doesn't take for itself and dissipate itself. And therefore, if it has a higher kinetic energy dissipation, fluctuations are less likely to be driven. Therefore, you expect that atmospheric flows will have higher kinetic energy dissipation subject to stability constraints. Okay, so this is assuming, of course, a fixed input of kinetic energy into the a fixed kinetic energy generation, basically. So that's okay? So let's say on short timescales, you could imagine like a fixed sort of temperature field over the Earth, and then the velocity fields will sort of structure themselves based on that, based on this principle, hopefully. But yeah, on longer time scales, it's known that it's a lot more complicated than that. So this here is GCM simulations varying sort of different parameters. So this is like a kind of a mixing parameter. This is a cloud parameter, and you can see that the sort of the contours are this energy correction, which is essentially a measure of the total kinetic energy in the Earth system as a whole. And you can see it's changing when you change these parameters. So by changing the overall structure of the Earth's climate, as you know, the global circulation overall changes. So in other words, here, you can't really assume on longer timescales that this input of energy is constant. So this raises the question of what governs the generation of total available potential energy to drive kinetic energy flow. And so this goes back to sort of Lorenz's argument. So he for a while advocated a type of a maximal kinetic energy dissipation argument for the atmosphere. And this is the famous Lorenz energy cycle. So you have the pressure drives kinetic energy, then that dissipates back, and you have this external heating coming from the outside to drive it. And there's a sort of feedback with the frictional heating. So this raises the question, if we've got a sort of a principle for the flow given a kinetic energy input, perhaps if we extend the equations and include the contributors to the drive, perhaps we can make an analogous stability argument and perhaps formulate a simple kind of a functional that you could used to predict the broader structure of temperature and all of that. So yeah, I'll just wrap up. We're also hoping to kind of, oh right, so yeah, when Marcus maximized, as I showed you, there were those two stability constraints of the Rayleigh criterion and the other one. It's not clear exactly what they would be for an atmospheric flow, so we want to look into that. Suggestions would be welcome. And yeah, we'd like to really think about how this picture fits in with more sort of statistical mechanical approaches, where you don't actually consider stability at all, you just consider phase volumes. But it seems to be leading to the same outcome. So we're wondering if there's some sort of connection in the reasoning that we could exploit and reveal something interesting. But yeah, open for suggestions. That's it.
Thank you. Any question, comment? You say you basically need some constraints. Is that the thing you need in this theory to sort of turn an overall principle of maximum kinetic energy dissipation into something useful?
Yeah, well, okay, so...
The question I got from this morning.
Okay, so if you look at, like this case, for example, so this was Marcus's optimization. The dissipation, the kinetic energy dissipation is essentially a measure of the average gradient of this profile, the blue line, essentially. So if you were to just maximize that without any additional constraints, you could imagine some like really sharply peaked, jiggly thing. So you essentially need constraints to keep the profiles reasonable. So essentially the argument just tells you it'll push towards higher kinetic energy dissipations, but you need to put in some physical details of sort of which profiles are actually reasonable. So it's like another level of stability, I guess.
You need something that knows about the Earth's rotation, I would think, otherwise that's...
Say again?
Well, obviously one of the big constraints over the solution you get in the atmosphere is the Earth's rotation.
Yeah, right. Well, yeah.
You need to know about that.
Presumably that would come in somehow, yeah. Yeah.
Like potential vorticity conservation or something like that.
Yeah, because you'd be inferring the full velocity fields in 3 dimensions, so for that to be realistic, you'd definitely need a Coriolis term of some kind.
For a question? Yeah, maybe it's a similar question, but for flows that are dominated by the Coriolis term, the energy cascades towards, well, there's an inverse energy cascade from small scale to large scale, whereas the pipe flow you're talking about, it's the other way. So it's hard to see that I mean, the energetics of the sorts of flows that you're looking at are very different. So it's hard to see how the same laws can apply.
Well, I mean, this equation here is just so, it's just literally the kinetic energy balance of the flow. So it's hard to see how it would be violated, in fact. Like, the heart of the matter is just that the fluctuations aren't driven by anything except the mean flow. And so, as long as the mean flow is wasteful, it's hard for it to drive fluctuations on top of it. But you need, it's true that you need to put in additional, so this just tells you that there'll be a tendency towards higher kinetic energy dissipation of the mean flow. But
you don't mention potential energy at all. You don't have a buoyancy term in there.
In here, this G is gravity plus the centrifugal.
That's a constant, though, right?
No, because it's got there's a U in here because there's a centrifugal component as well. But yeah, okay. So there's no buoyancy in this at the moment because rho has been assumed constant as well. That's true. So yeah, I'm not sure if that would substantially change this although.
Well, I mean, the energy can go from kinetic to potential. There's a lot of energy in potential energy. A lot of the mechanical energy, for example, in the oceans, is potential.
Yeah. Okay. So that's all of that is determining what this term will actually be in the real world. This argument is just saying if you have some kinetic energy input into this fluid, because the fields are kind of smooth, they can't drive these sort of fluctuating fields. They can only be driven by the mean flow. They can't be driven by that energy directly. And so the mean flow acts as a kind of a gatekeeper. And if it's wasteful, the fluctuations will struggle to live, basically. They'll struggle to grow. It's just as simple as that. Getting a handle on this term is definitely the next step if we want to actually make predictions about the actual climate, because that thing is changing the whole time. And there's like feedbacks as well, because the circulation obviously changes the temperature gradients. And I don't know if that answers your question.
Is there any further comment or question? If not, thanks again, Jason. And we move to the final paper of today.